Hi guys, hope all of you are doing great. My name is Ernest. I'd like to welcome each and every one of us to our channel of Ernest Sciences and Mathematics TV channel. In our channel, we discuss different aspects of mathematics and sciences. So today we are going to look at this interesting topic on atomic orbitals on carbon. And this is going to open for us a window of trying to figuratively describe the concept of reactions, especially in organic compounds. So in this case, I'd like to welcome us all and invite us to subscribe to our YouTube channel. Kindly engage us on the comment section so that we can have your feedback on our various topics and try to assist one another. So without further ado, thank you and welcome. So as I've said, our discussion today is going to be centered around the atomic orbitals on carbon. Now, in our earlier videos on the introduction to organic chemistry, we had mentioned various relevance of this particular compound, or rather various this particular element that we had referred to as carbon. And we said that carbon in its own nature is one of the diverse compounds that displays diverse characteristics. And that is why it's being relied heavily, especially on this particular concept of organic compounds. Now, in our discussion for today, I'm going to introduce this specific part by having a summary of the concepts that we have discussed in our earlier introductory video to organic chemistry. And this is going to assist us, of course, in understanding the overall, our overall objective for this particular discussion. So in essence, we said that we can be able to represent carbon using this particular illustration for an atom of carbon. So in this case, I'm going to have this figure given as uh, those electrons and the two energy levels. So I've got this electronic configuration for the carbon being given as the first energy level for 2 electrons and the second one for 4 respectively. And there were various ways in which we were able to represent this carbon atom, which of course is going to display different characteristics whenever it is going to be associated, or maybe it's going to experience bonding and maybe reaction with other elements. But we said that in order for us to have stable compounds, there was a concept of the octet rule, whereby from the periodic table we had seen that elements which were the far or rather the extreme left of the periodic table will rather lose their electrons, valence electrons, to react with other compounds. And elements that were at the extreme right of the periodic table preferred to gain electrons in order to. So I'm just going to use that rough illustration. So this is to the right part of the periodic table, and this is to the left part of the periodic table. And at the center here, we have specific elements which of course have valency of 4 electrons, like one of our examples that we are using, like carbon. So in this right side, of course, these are elements which gain electrons whenever they are reacting with other elements to form compounds. And this one loses electrons in order to form compounds. And this generally on our periodic table on the left, it consists of alkaline earth metals, and some of the transition elements that of course are being exhibited at this left part. And this one we have, of course, apart from the noble gases which are not going to, of course, experience, we have halogens and other compounds which of course are going to gain electrons to form compounds. Now in this case, we're going to see that carbon will rather form covalent bonds with other compounds in order to other elements in order to form compounds, instead of losing or gaining electron, as we can see, to obtain the octet rule, which in an actual sense refers to the concept of 8. So in this case, this is a centrally placed element which is going to share its valence electron covalently with others. Therefore, we give an illustration for this particular case, whereby we say that we can give one example of this using an electronic dot notation, whereby we say that if carbon has got valence electrons which are 4 in number, therefore if it is going to form a compound through addition of perhaps hydrogen which has got a single electron, then therefore it's going to gain 4 hydrogens to form a compound like methane. So therefore we're going to see that an hydrogen is going to donate 1 electron to form a bond with carbon, and then the subsequent hydrogens are going to just have the same display of that particular behavior, and therefore we're going to represent this kind of bonding using these two shared pair of electrons as such. Now in this case, of course, we could as well represent this particular molecule using the carbon and the 4 strokes for that bond, covalent bond as such, therefore illustrating the concept of that formation of that compound from carbon and hydrogen. So therefore these atoms are linked, can be able to link, of course, with other carbon atoms, and these are going to form strong stable covalent bonds as I've mentioned. And therefore, due to the characteristic of an atom forming stable bonds to many other elements, we're going to see that this is going to than or a wide range of compounds which carbon has been shown to form compounds or rather form more than 16 million compounds, whereas the other elements, of course, which are going to be compared to carbon, are going to form elements ranging between 600,000 and lower number like that. So in this case, this gives carbon a characteristics of having a diverse use, and therefore standing out as a central element, of course, in organic chemistry. Now, as we have mentioned that, of course, we are going to see that the ability of carbon to form several compounds, of course, had given us a clue on how we can be able to represent different organic molecules. And as I've said that carbon has the ability to form compounds with other carbon, of course, hydrogen, fluorine, chlorine, and it can also bond with bromine, iodine, oxygen, sulfur, phosphorus, and from this particular case, we can as well see that therefore we're going to have a huge range of compounds which are going to result from that. And then next we said that it can be able to form complex structures, which of course we said include structures such as the long chain and the branched structures, chiral compounds, and other complex three-dimensional shapes that we're going to see later. Of course, we're just going to have a summary of that. That in an essence gives us a characteristic of carbon that we're going to see being displaying different characteristics insofar as atomic orbitals and interaction with other compounds are concerned. Now, of relevance for us to discuss this is the wide applications of carbon that we find in our society. Part of them, which of course are natural derivatives like vitamins, carbohydrates, lipids, proteins, enzymes, energies like adenosine triphosphate, DNA, and RNA, which are genetic molecules. And therefore, we're going to see that it can be applied in various areas of technology, therefore giving us a basis for having an emphasis on this knowledge of atomic orbitals on carbon. Now, having said that, we're going to look at, of course, in various ways, and that is going to give us, of course, a summary of what basically we're going to discuss. And I've said that carbon atom, of course, does not form ions due to the valence electrons, which we had given the electronic configuration as for C4. Therefore, it prefers to bond covalently with other carbons or other elements to form compounds. Therefore, we have already discussed on how we can be able to assign electronic configuration for different elements, and then therefore using the Haken rule and the other Hans rule and the other, of course, Aufbau principle, we can be able to write the electronic configuration of this specific atom using the first orbital for S, and the 2s orbital is going to consist of 2 electrons, and then lastly we're going to have the 2p 2 electrons being given as such. Of course, we have decided that this one can be written in different versions, but we're just going to have that one displayed as that for just emphasis. Now this is going to, of course, share electron, as we have said, to attain the octet state, and we can as well use the energy level illustration for us in order to display this particular part of the carbon, whereby we said that energies are filled from the lowest part to the highest. So therefore, at this lower part, we're going to have the 1s orbital, and then next it's going to be followed by the 2s orbital, which is basically going to be followed by the 2p orbitals as I've arranged in that specific order. So this basically is implying energy. So therefore, we're going to see that the 1s orbital is going to be filled using the 2 electrons. So therefore, we're going to have those ones depicted as such from the magnetic, the spin that we had already discussed in the magnetic quantum, or rather quantum numbers that we had discussed in our earlier video. So the next orbital as well is an s orbital. So therefore, it's going to be filled by those 2 electrons. And we're also going to see that the remaining, this is the first 2, the second 2, and then the remaining 2 electrons which are going to fill the p orbitals are going to be displayed as, so the p orbitals, we said it consists of 3 orbitals. So using the rules that we had discussed, of course, these are going to be 2 electrons which are going to be shown like that for the x, y. So the z orbital is going to be empty in that respect. And in this case, for the, we have already discussed the shapes of different orbitals, and we said that the s orbital is circular as such, and then the bubble, the p orbitals are going to be displayed as the bubble, which is going to be indicated as this. I hope that my pronunciation is okay. So it's going to appear just like this. So this is going to be the p orbital, which is going to be contrasted with that as much as I've just illustrated them as such. This is an illustration of how the orbitals generally appear, as we had discussed earlier. So these orbitals are going to exist as or be illustrated as this. Now for compounds like carbon to form the other complex compounds or interact with other compounds to form covalent bonds, as I've said, we're going to have what we call a mixing of orbitals, which basically we refer to as hybridization of orbitals in order to form stable compounds. Now this is going to be according to Linus-Pauling, which we are going to discuss in our other videos. The Linus-Pauling principle is going to give us a clue on how this hybridization of orbitals or mixing of orbitals is going to occur. Now, as we have said that these electrons are filled according to the level of the energies of those specific orbitals, we're going to see that when carbon atoms bond to other atoms, the 2s orbitals and all the 3p orbitals that we have given in this particular case. Now in this case, the 2s orbitals, we are referring to the first and second one, and then the 2p orbitals are going to form of course part of these orbitals in this carbon atom. But for the last 2, which is the 2s orbitals and the 2p orbitals, are going to form part of what we refer to as the valence shell. So this is the first shell, in this case for 2 electrons, and then the 4 orbitals, the 4 electrons are going to be contained in what we call the valence shell of this particular carbon atom. So in order for them to bond to other orbitals to form a hybridized molecule, we're going to see that this can be illustrated using, just have an illustration of what is happening during this bonding. So we're going to have an illustration of the 2s orbitals and then bonding to form a hybridized 2s orbitals, the 1s orbital, the 2s orbitals and the 2p orbitals are mixing to form what we call a hybridized orbital, which I'm going to give an illustration shortly. So we're going to have the valence shell combined to produce 4 sp3 hybridized orbitals in this particular case. So we have our 2s and 2p, which are valence shells which are going to combine. in this specific order to form the sp3 hybridized orbitals. Now, in terms of an energy level, we're also going to illustrate this one using this specific illustration. Now, from this energy level diagram, we're going to see that this valence orbital from this specific point is going to be promoted to an sp3 hybridized orbital, which is going to contain the same, of course, possess the same energy, which is going to be basically at the same energy level, of course, with all these other orbitals from these 2p orbitals that we have seen in this particular case. Now, these are going to contain 1 electron each in this specific hybridized orbitals that we're going to see in this specific case. So this process is referred to as hybridization, and we're going to see various ranges of this particular bonding, whereby it's going to include hybridization of orbitals of these carbon atoms with other elements as we proceed. So basically, this is going to give us a clue on how we're going to describe various the compounds, like the organic compounds, using this specific case for hybridization of orbitals, whereby these valence shell electrons are going to react with other or bond with other elements in order to form hybridized molecules, which we're going to see later. Now, in our next video, we're going to see the hybridized orbitals and shapes of specific compounds like ethane, which are going to form bonds with other compounds through this process of hybridization. So catch us in our next videos. We're going to look still at the advanced or rather the next topic, which subtopic under this category of atomic orbitals on carbon, which specifically I've said we're going to give examples and try to see how this one is going to happen. So in that case, that is it for now, guys. Bye. God bless you.